All right, so we'll take a look at some of the questions from this week's content, where we're looking at electrons, periodic table trends, etc. So the first one here, we're going to take a look at electron configuration. So in this example, we're given 1s2, 2s2, 2p6, and then 3s1. All right, so remember now in your electron configuration, the way that these look, this first number here gives you the principal energy level. The second, which is a letter, either S, P, D, or F, you can think of those as a sub-level. And then the superscript, that is the number of electrons. All right, so if we just add together these electrons, we have 2 plus 2 plus 6 plus 1, that gives a total of 11 electrons. And we're told that this is a neutral atom. Okay, so we have 11 electrons in this atom. Now, atoms by definition are neutral overall, which means that the number of electrons should equal the number of protons. So if I have 11 electrons, guess what? I should have 11 protons, and the number of protons is the atomic number, and that atomic number identifies that element. So all we need to do is to look up on our periodic table and find element with atomic number 11. So there's our periodic table. And that looks like atomic number 11 is going to be sodium. So our element here is going to be sodium, Na. That's our chemical symbol. How many electrons does the atom have? Well, we just figured it out. We just added together the superscripts, 11 electrons. How many 2p electrons are in the atom? Well, we just look at our configuration. So we look for the 2p designation. We have a total of 6 2p electrons. All right, now we're going to take a look at writing the electron configurations. Using the periodic table. Okay, and there are a couple of ways that we can do this. We can do the shorthand notation. We can do the regular longhand notation. So let's take a look at a periodic table and see how we can use it actually to determine our electron configurations. All right, so in this particular question, we want to determine the electron configuration of this atom here. So this atom belongs to, looks like period 4, group 1. So on my normal periodic table over on the left side, I can find period 4 says period 1, 2, 3, 4, and group 1. So that'll be K. The identity of the element is really not that important in this particular question. We need to be able to write the electron configuration for it. So let's take a look at how we do that using the periodic table. We can break the periodic table up into several blocks. This first block here in blue, this is called the S block. The block in green over on the right side, the last 6 columns of the table, this is known as the P block. And in the middle, in yellow, we have the D block. So we can use that, and underneath, by the way, over here, this is the F block. And these correspond to different sublevels in electron configuration. So how do we actually get to electron configuration of this element here? So we always start at the top left and work our way across to get to the end of that particular row. So the first row is the first energy level, and we have to go through that S block, which is usually made up of 2 columns. So 1s, and then we go through those 2 columns. Now, typically, we would have this helium over here to show that that block we need to traverse all the way across. And we put the number of elements that we need to go across as our superscript. So 1s2 gets us to the end of the first period. Then we get to the second period. So now we go 2. We have to go across the S block, and we have to go across 2 elements. So 2S block, 2 elements. Then we jump all the way over to the P block now, and we're still in the second row. So 2 P block P. We have to go across 1, 2, 3, 4, 5, 6 to get to the end. So 2P6. And we get to the third energy level. So now 3. We have to go across the S block, 1, 2. So 3 S block, 2 elements to get across. Then we encounter the P block on the third energy level. So 3 P block P, and we go across 1, 2, 3, 4, 5, 6 to get to the end. Then we're in the fourth row, the fourth energy level. So 4, we go across the S block, just that first element to get to, in this case, is potassium, 4s1, right? So this will be our electron configuration for this element. This is the full electron configuration. We can do an abbreviated or noble gas configuration, where we find the element in question, which in this case is the potassium over here. We go backwards now. We find a noble gas that came before it. That would be, if I backtrack, that would be argon over here. So I just take argon and I put it in square brackets, and that automatically takes care of all of these electrons. Those first 18 electrons are automatically accounted for. And then all that's left is my 4s1 to get to potassium. Okay, so either way would work to get to your electron configurations, and that's how we can use the periodic table to help us quickly determine those. All right, and then we have another question that allows us, so that asks us to identify the different blocks of the periodic table, S, P, D, and F, like we just mentioned. So we just highlight, get your highlighter selected, and then the S block, first 2 columns. We'll go ahead and highlight those. All right, and then we're missing an element here. So typically helium is included in that, because again, that finishes off that second electron in the S block. All right, so we're looking now at some of the trends in the periodic table. And the first trend that we're looking at is ionization energy, which, remember, is just a measure of the amount of energy required to remove an electron from that particular atom. And the trend in ionization energy typically is as you go up and to the right, the ionization energy, IE, that's how we abbreviate it, increases. Okay, so all we need to do is to find our elements on the periodic table and just compare them to see where they actually fall in that trend. So we have magnesium, Mg. We'll highlight them. So Mg is here. We have what else? Rubidium, Rb. We have cesium, Cs, and then we have sodium, which is Na. All right, so according to our trend, the element that is further up and to the right will have the highest ionization energy. So magnesium would be the highest. The lowest would be further to the left and down. So that would be cesium would have the lowest, and then we can work our way up from that, right? So we'll have, depending on your point of view, magnesium the highest, then sodium the next highest or second, rubidium the third highest, and then cesium would be the lowest or the fourth highest. All right, so let's see. We said magnesium was 1, sodium is 2, rubidium's 3, and cesium would be 4. Let's see if that's correct. All right, so that's a trend in ionization energy. All right, so the next thing that we're going to do is take a look at the trend in in atomic size or atomic radius. And the very general trend that we're going to see is that the size of the atom increases as we go from right to left, and then from top to bottom, right? So atomic size increases in the general direction, sort of to the lower left side of the periodic table. So again, if we want to take a look at the elements that are provided, so we have, let's look at the first one, B, boron, neon, and oxygen. So we find those, boron, neon, and oxygen, right? So they're all in the same period. And as we go from right to left, the size is going to increase. Okay, so that means then that boron will have the highest, the largest size. Oxygen will be second. Neon we expect to be last. Let's take a look here at the third one, bromine, the selenium with looks like a charge or something on it, and then the selenium atom. All right, so if we find those, we have Br, so bromine, and we have selenium. All right, so again, if I just compare bromine and selenium, comparing these two, bromine will be smaller, and selenium would be larger. It's further to the left. And then we also have this other thing, this Se2 minus, right? So what that means, if you notice here, that has a negative sign on it. That means that there are extra electrons. Okay, and if there are extra electrons, those electrons take up more space, right? So they need to get into that atom. They're going to occupy more space. The atom's going to get bigger, so it'll be larger than the corresponding neutral atom, Se. So if I need to compare those three species, those three chemical species together, right, the largest then would be the selenium with the 2 minus charge. That'll be greater than the Se, and that'll be greater than the Br. All right, so you'll see a couple of these. That's how you want to interpret those. All right, so we have B, O, and Ne for the first one, and then the one that we just did over here as well. All right, so next one we'll take a look at is some of the relationships and the organization of the electromagnetic spectrum. And we're given in this question several different types of radiation that we would find in the spectrum, and we need to order their frequency, their wavelength, and then their energy as well. So I have here just a simple picture, a representation of the spectrum with some relationships. This is in your textbook. You can find it online, etc. So the first thing we need to take a look at is the frequency initially. So right off the bat, we'll just give you a couple of relationships that you need to be aware of that you'll find helpful as you go through these. Okay, so the frequency is proportional to the energy. Okay, so what I mean by that is if the frequency, remember frequency has a symbol that looks like that, that's pronounced nu. If the frequency goes up, that means the energy is going to go up as well. And similarly, the frequency goes down, the energy is going to go down. All right, so the first relationship. So if you know one, you can kind of predict the relationship for the other, or the corresponding change for the other. The other relationship we need to know is that wavelength and frequency. So wavelength is lambda, the symbol looks like an upside down Y, and frequency are inversely related. Okay, and what that means is if the wavelength goes up, okay, the frequency nu is going to go down. And we can sort of use now what the first relationship to tie that in. If frequency and energy are directly related, then we can say also that now wavelength and energy are also inversely related to each other. Okay, so what that means is as or if the wavelength goes up, the energy is going to go down, and vice versa. If the wavelength goes down, the energy is going to go up. So it's a simple, or not simple, but it's a not a convoluted relationship, but it's important to know. And that's manifested here in our table. You can see as the wavelength, as you increase the wavelength from left to right, going from gamma rays all the way over to radio waves, for instance, we see that the energy actually decreases going in that same direction. Similarly, as we decrease the wavelength going from right to left, we see that the energy is increasing as well. Remember, energy you can think of as having the same sort of relationship to the frequency. All right, so infrared radiation, radio waves, X-rays, green light. So you want to find all of these types of radiation on your spectrum. So infrared is right about here. Radio waves is further on the right side. X-rays are way over to the left, and then green light is part of the visible spectrum. Okay, so we have, if we want to chart or highlight those different regions, we have our X-rays, we have green light over here, somewhere in the middle, right about there. We have infrared, and then we have radio waves. We're just going to compare them. If you look at the frequency and energy are going to have the same sort of relationship. So the one with the highest energy would be our X-rays. That'd be the highest. Same thing with the frequency, the highest. Oh, wait a second. X-rays are down here. The highest would be that one. The lowest will be our radio waves. So we can then go ahead and plug that in. So that'll be the lowest, which is 1 for both the frequency and the energy. The next highest energy and frequency would be the visible light, which is going to be our green light in this case. That'll be 3. And our radio waves, our infrared, sorry, are going to be the third highest. All right, so let's put that in. Or second lowest, if you want to think about it that way. And then it'll just be the opposite or inverse relationship for the wavelength, all right? So the thing that has the highest wavelength is going to have the lowest energy. Similarly, the highest energy is going to have the lowest or the shortest. Well, in this case, it'll be the wavelength would be the longest, if you think about it that way. So the longest wavelength, okay, so longest wavelength would be our radio waves. So longest, so make sure that you match up the numbers to what the descriptions actually mean. Next would be our infrared, so it'll be 3, and next would be our green light, which would be 2, and then the shortest wavelength would be our X-rays. All right, so it'll be 1. So let's see, we got our numbers. Let's see if that works. So you need to have your spectrum available close by to sort of as a reference, and then just being aware of the relationships between energy and wavelength, energy and frequency and wavelength, etc. All right, so now we'll take a look at how we can quantitatively relate those features of waves that we saw previously, meaning that we're going to do some calculations. So here we're going to be converting between wavelength and frequency, and we're going to use a wave equation to help us do that. So remember, frequency and wavelength are related to each other via this equation. So if we multiply the wavelength times the frequency, we end up with a constant value c, which is the speed of light. Okay, and that's a constant. It's a constant value, 2.99 times 10 to the 8 meters per second. That constant will be provided to you if you need it in any calculation or quiz or exam or anything like that. So if we are given any one of these two other variables, we can rearrange that equation to solve for any of them. So for example, the frequency would be equal to c over lambda, or the wavelength lambda would be equal to c over the frequency, right? We can rearrange the simple algebraic expression to solve for any of those two variables. So in this particular example, we're told that radio waves have a frequency. So we're given frequency as 88 megahertz. So 88 M, big M, Hz, that's megahertz. Okay, so recall now, hertz is the same as second to the -1 or 1 over second. And mega, we've seen that metric prefix before, is 10 to the 6. All right, so what we're saying then is that this is 88 times, I know it's not expressed in proper scientific notation, but this is what it would be. 10 to the 6, that's mega, and then hertz would be over second. Okay, that's in a way, expressed in a way that would be useful. That's what it actually means. We need to calculate the wavelength of these radio waves. So we need lambda in this case. All right, so I can rearrange my equation. Lambda then is equal to c, speed of light, over my frequency. Okay, and remember now, I want to get it to with that seconds as the unit, because the speed of light that I'm using has seconds as one of the units, right? And we're going to need that to make sure that our units cancel out. So speed of light 2.99 times 10 to the 8 meters per second. And I'm going to divide that by the frequency 88 times 10 to the 6, and then that's per second. Okay, so if you think about it, this is the same as saying 2.99 times 10 to the 8 meters over second divided by 88 times 10 to the 6 over seconds. If I simplify that, I have 2.99 times 10 to the 8 meters over second. I divide by this, that's the same as multiplying by the inverse of that, seconds over 88 times 10 to the 6. So what you'll see, right, is that the seconds cancel, and all I need to do is to evaluate this now using my calculator. So my wavelength, 2.99 times 10 to the 8 divided by my other value, and then my unit, the only unit left is meters. That is a unit of length. Guess what I needed to find? A wavelength, right? So the units make sense. All right, so if I evaluate that, plug it into my calculator, I get 3.39772 ... And then meters as my unit. I want to make sure I round this to the correct number of sig figs. I use the speed of light, and I use this value that was measured. So this has essentially an unlimited number of sig figs. This one has 2 sig figs. So my final answer then needs to be rounded to 2 sig figs. So this would be, looks like 3.4 meters as my wavelength for that particular answer, right? So we can use the equation C equals lambda times nu to solve for any of these unknowns if we're given the other thing. The one thing you want to be careful with is to make sure that you keep track of the units, because you want to ensure that you're using the correct unit so that they cancel out when you set it up and you do end up with a unit that's required in the problem.